questions now. I mean, I just put it out. If it was showing
How you
me, I
got
could
the
have So
There you go. That's why. That's all. That's why I was thinking. It's like the homework really helps.
that's my moral. I still have to make my website. And my first missed this one, but
What y'all wrote about? Another cracked up. This is the last supper. I saw Mason, I have a picture of you. I don't even know when it does.
it's not the final dinner.
Okay. This is our side. Yes. This is forget. I'm trying to figure out Face's name.
No, right? You're so happy too.
No, but I do, but I can't remember. No, this is not reading I wrote. Are you incapable of reading? That's a little rude now.
After saying that, you'll look at somebody as
Why is there hair, dark hair on my desk? It's fine, I lost it to 70% of my knowledge here, so. Yeah.
Oh shoot, there's Mike. I think I'm so dumb. I brought my compass, my switch. This is a good compass, man. It's like explaining this to him. He was like, I was like, I set that up perfectly. I couldn't reach all my circles.
Also, I'm not switch charts too.
There's 3 ones in the ELEC. Oh, really? Yeah, they
I might need to pick up some. Yeah, if you get on one after.
yeah.
I printed out a bunch yesterday and I set them on my calendar.
Yeah, the
Like the lights are never on here.
So I'm going to start with questions about any homework problems, and then I'm going to get into math. Now, if you've done it, I mean, most of the stuff kind of becomes obvious if you do the homework problem. Any questions? You all got it? How many feel good about that? Does anybody have a question? I'm looking at, I don't know.
I don't have my book, but there's 2.31 from homework. Yeah, like that.
All right, 2.31, you said? Let's take a look at it. Look through it together. Get your Smith chart out and get your straight edge and compass. So it's 2. All right, 2.31. I'm sorry about that. I didn't see that. Go ahead. Tell me, can somebody just read the prompt to me anyway? Say again?
Figure 2.356 is shit. I'll have to give you the figure.
I got it. Is this the one with the, they got a measurement across this, an actual line? Okay. Who asked me about this in my office? You guys did? Okay. The problem is, I can't replicate this from on the board, but I can estimate it. It's a good problem. Let me try. I don't want to go down there and start this again. 2 point. All right. figure 2.56. Now I'm going to show you something about this. Don't let this stuff get you all frazzled. So first, I'm just going to draw a transmission line. Here's EL. We have some C naught. Just leave it as such. And a Smith chart. Now I'll try to estimate what they have, and I want to tell you what they're doing. This is an old, back in the day, probably 30 years ago, 20 years ago, what they had were laboratories, and they do measurements, just like in physics labs. And what they're doing is measuring the voltage between the inner conductor and outer conductor on a transmission line, and they're giving you the actual measurements to look at, and then from those measurements, estimate the values. I think they want the load impedance, and I'm not sure what else, but you all follow me on this? So if you look at this, and I'm going to try to estimate this thing, they're going to have something, and the first thing they're going to have is a diagram of something with a short circuit. Do you all hear? You all follow me? How many read this problem now and are familiar with it? You guys, you have not seen this problem? Did you do it? No? If you didn't do the homework, you're hurting yourself in a big way. But they put a short circuit where the load is. Do you all hear me? That's what they do. And you're going to get something that looks like this. Are you with me? Now, this is on this side, this is the voltage magnitude measured between the inner and outer conductor of a transmission line. How many understand what I'm talking about right here? Let me just see your hands. Okay, if you didn't do the homework, listen carefully. He's measuring the voltage from the inner and outer conductor. This is the magnitude, maximum magnitude. Anytime you have a short circuit, you know you have 0 volts. Do you all hear me on this? So the load is somewhere, probably here. All right? And you can take a look at that. What is the value? And you're going to have to eyeball this one. Give me a value. It's in centimeters. I forgot what it is. It's not 0. It should be 0, but it's not. What is it? Just look at the bottom. You got a book?
Scales tend to 0.
I know. What's this value here where it goes to 0?
Like on the y-axis?
This is the x-axis. Tell me what this value is where it goes to 0. Can you all see
Oh, I
it?
see what you mean. Yeah, it's like 1.1, 1.2.
Centimeters. How many see this? Can you see it back there? If you've got a book, get it out and take a look. So this is about 1 point, is it 1.2 or 1.1? 1.1? 1.1 centimeters. Now, this is the next point it goes to 0, right? What's that value?
7.5.
All right. Is that approximately right? You guys were in my office. Is that right? Now, every time, just listen to me. If you think about this, I've got a short circuit. I go through a maximum to a minimum, right? How far is that in wavelengths, class? Exactly half a wavelength, right? Remember that every time you're taking a look at the voltage maximum, it goes to a max. You're going to get to a maximum at a quarter wavelength away, then a minimum. If it starts at a min, it goes to a max at a quarter wavelength, then a min at a half wavelength. You all with me? Now, what does that tell you right off the bat? Because this is a good problem. This tells me lambda over 2 is equal to 7.5 centimeters. Is this right? 1.1? This is odd numbers if they gave you that. So if you take this, the wavelength, this is 7.5, this is 1.1 centimeters. The difference is going to be what? 6.4 centimeters? Is that right, class? Is that lambda over 2? Is that right? You were in my office doing it. Did you? Is that right or not? You forgot? All right, we're going to assume it is. I'm going to assume it is. All right? That means the full wavelength is what? It's 2 times 6.4 cm. Right? And what's that going to be? 12.8 cm? You have the answers. Is that the answer he gives in the book?
Yeah. Or I think they might do 12.6.
All right, and this is eyeballing too, by the way. These are not, he did not blow this thing up to give you an exact, but everybody follow me, and the reason why. So this is, we'll call it 12.6. I'm going to just assume that this is 12.6 cm. All right, now you know the wavelength. With And you know actually where the load has to be, because he takes the load off and he replaces it with a short circuit. So it's likely right here. It's close to that point. You with me? That's the load. Remember that. That's the load. Now what I'm going to do is draw on top of this and superimpose on this the actual value of the voltage that exists when the load is put back, the voltage measurement. So it does something like this, and you're going to have to forgive me, but it does, does it go to a min here like this? It does something like this. Oh, well, that's not drawn right. It's going to do something like this, and this is an exaggeration, but you all follow me in this? Take a look in your book. You with me? Now that's the voltage magnitude versus position for the actual load. This is a real simple one. If you look at the maximum value here to the minimum value right here, you get the ratio of that V max to V min is the standing wave ratio, right? So what's the maximum value? I think it was about 4 and minimum about 2. What is it?
2.
The maximum.
Well, max is 4, minimum is 2. So
all right, so it's 4 over 2, or 2. You all with me? Now, with that, you have a critical piece of information. Do you know the radius of the circle for the reflection coefficient that we're about to draw? Remember, this line, when we come out here and put where the load is, and then we go ahead and take this compass and go around it, that's the magnitude of the reflection coefficient. You all hear me? Now, where it crosses this point will be the standing wave ratio. So if you look at this point, you're going to see a 2 on your Smith charts. I hope you have them out, class. I'm going to warn you about this. Getting behind in this, you'll kill yourself. I mean, you will get zeros after zero on quizzes if you don't stay up with this. And I see this all the time. Yeah.
Do we need to bring in our own Smith chart for Friday's test?
Well, yeah, why not? I mean, I gave you a bunch, right? And they're good ones. Just print it out without scaling and bring them in, all right? By the way, how many people are from Florida here? Anybody? One? Just one? All right, this storm has made landfall and is pushing through, and I don't know if anybody's going down there to help their families out. Somebody asked me also about Labor Day being Monday. Would it be all right if we postpone the quiz to Wednesday just because of everything going on? All right, if you don't mind the quiz on Wednesday, raise your hands. Shocking. But you know, how many are staying here for the game? All right, well, whatever you want. All right, now look, guys. I estimated where that was. Take a compass and draw. And here you're going to draw a circle of that radius. We did this together. I forgot when, but we did it. Right? You with me? Now you've got the circle that is the magnitude of your reflection coefficient. The load impedance is somewhere on there. You all with me? It's the point where we normalize, we come in. Now, what you'll notice is this, and I've told you some things about this. If this is our circle of load impedance here, this is constant gamma, right, magnitude. What you know is when the load, or when you move this, just assume this is ZL here, normalize. When you move and hit this point, that's a voltage maximum. Write it down, voltage maximum. And exactly a quarter wavelength away, right here, this is a voltage minimum. Now, what do I mean by that? It means wherever the load is, as we move away from the load, this is a normalized load value. When we hit this point, remember, you would throw a line up here and you would read the mile marker, the wavelength torque generated. When you come to this point is the maximum. You all hear me on that? Keep going, and this would be the voltage minimum. Now, I didn't draw this to scale, but somewhere there's the maximum, right? And here, I'm sorry, this is the maximum. This is just my drawing, right? So the maximum right there is associated with this point. You all with me, class? Now, I gotta look at this thing. I'm not a real fan of this one, and the reason is the resolution's horrible. You have to eyeball things, and it's hard to get down to fractions of a value here. But in this one, he shows the voltage minimum actually. Let's see. Where's the load is at 1. Gosh.
Power test.
Yeah, see, it is the second.
Yeah, this week won't.
Yeah, they are. I just hear like the not guessing full.
Tell me how far away it is. Guys, we did this one, right? So, how far? Just tell me from this point. Tell you what, did we do it? We did it to the voltage maximum or minimum? I forgot actually. I'm sorry. I did this one of these, and the solutions are there, right? Let me try to talk you through this if you don't know what I'm saying. All right. You all agree I can get the position of the load from this right here, this when the short is there, right? Now, when I take a look at the tracing out of the actual value of the voltage, all right, I mean the actual voltage, it does this thing. So the load's here, and when I trace it out, how far is it? Well, from here, how about between? Oh gosh, did we hit a max? Did we go into a maximum or a minimum? I forgot actually. Do you remember? I had a bunch of you in my office. Was it maximum or minimum?
I don't remember.
Well, here's what we need to do. If we know this is the actual point where the load is, right? Then, if we have a voltage max, just think about this. If we're saying it's a voltage minimum next, try to think. Actually, let's go to the voltage maximum. Can you tell me the distance? It looks like the voltage maximum is at 5 centimeters on mine. So it's 5 minus 1.1, right? Is that's 3.9? Is that right, class? Did you get about 3.9 for that? Or not? This is on the one with the standing wave ratio. I got that. I'm getting about 3.1, right? Correct, class? Yeah. All right. The voltage maximum would occur on the Smith chart right here, but now I know. I mean, you all with me on this one, class? And I know that I'm how far from it? I'm 3.9. Is that right? Roughly 3.9. So that means I have to go 3.9 centimeters. What is that weight? Here's what I'm trying to tell you is, what this gives you, when you take a look at this, we know the location of the load from the voltage minimum here. You all with me? Now the standing wave ratio gives you the radius of that circle. That's the second thing. Now, based on that, if you find the location of the voltage maximum or minimum, let's just say voltage max here, all right? I know that maximum value of voltage, listen to this point. This maximum value of voltage corresponds to this point right here on the Smith chart, all right? Now, if you think about it, if we're at that point and we're moving in that direction, we're going wavelengths towards load. Do you all hear me on that? We're at a point, this is where voltage maximum occurs. So how far do we have to move? And if you can tell me the distance between here and here, right? I said it was about 3.9. Is that in the book? Is that the right answer?
They said 3.1.
All right. My eyes aren't good. So if it's 3.1 centimeters, we have to divide that by the wavelength, which is 12.6 centimeters, and that gives you the fractions of the wavelength we're moving. Do you all follow me on this? It's fractions of wavelength. So what is this value? I don't know. Everybody understand the reason? Everybody start. Go ahead.
I got .075.
0.7, not in centimeters. This is a ratio. This is wavelength. We're dividing.
Oh, yeah, centimeters cancel.
Yeah, this is wavelength.
Oh, that's
0.75 wavelengths.
It's .711, I
711.
No.
What is it?
0.25.
0.25. 0.25? Is that right?
think. 2.46.
0.246. We'll go 246. All right. Now that's almost halfway around. All right. Every time you go halfway around, it's a quarter wavelength. So if you think about this, we know the maximum occurs here, and we have to move wavelengths. If you think about it, there's a maximum. Now we have to make, and that maximum corresponds to this point. Now we have to go wavelengths towards load, right? So if you take a look at this point, and then you move from there, what is it? Man, it's way over here, isn't it? Something over here, class? So we have to go to, so this total distance, that's 0.25, you subtract 0.0246 from it, you're gonna get something that's about, what is that? This is gonna have a mile marker of 0.04, right? Is that right, class? .004 right here. I forgot what that is. Is that right, class? Does anybody have a solution? I'm trying to go through this kind of quickly, but I'm trying to be careful about this. You all with me? But just remember this one thing. Try to understand it. I'm sorry this is drawn kind of messy. When you take a look at this, the first thing you do is locate where the load is located by that short circuit. Y'all with me, class? That's where your load is. All right. Now you put the load back on. Now I have this. See this? Everything? Yes, sir.
How come we didn't go a quarter wavelength from the normalized load? Where did we go the quarter wavelength?
We don't know where the load is, do we?
Okay.
Where do we know? And let me get at this way. We know that the load's here, right? Right. Now, we know the location of the load. We know wavelengths also. What else do we know? Once we do the measurement, we get this, and we see that the actual maximum here occurs at a certain distance from this point right here. Right? So from the actual location of the load to where the maximum is, you said it was, I forgot where it is. Did I erase that? 3.1 centimeters, did you say that? So this is 3.1 centimeters away. This distance right here is 3.1 centimeters, but in terms of wavelengths, which is the important thing, we divide that, we get 0.0246 length. Y'all with me? Now, here's the maximum. I'm at the maximum, right? And I know what happens is, wherever the load is, as I'm moving this way, I hit the maximum. Right, when I hit the maximum here, that's where it would correspond. I don't know where the load is, but I know one thing. The maximum is here, so if I'm moving towards the load, I'm going in the opposite direction. You with me? So I'm here, here's where it would be on this graph. You all follow me? This would be the, so I have to move in this direction because I have to go wavelengths towards load not generated in the opposite direction. And is this right, what the value I've got out here? He has it in his book, I'm sure, but what's the value he moves by? His solutions. Does anybody have a solutions class? How many tried this problem? I did it in my office with a bunch of, is that right? Does anybody have the solutions? Could you just look there, because this is all I need to know, because then we can get the load.
I'm pretty sure when I don't remember the exact number, but I'm pretty sure when we did it, instead of the line going up this way, it's below. I think I'm distraction.
Go.
Right here. I think
Could be reading this wrong, but I think it's 0.351.
What's that, the mile mark or what?
What he's talking about, where that line's supposed to be going actually like down and to the left.
Yeah.
Well, if we're here,
That's what we got in office hours. I just don't remember the value of it.
well, if we're here, right? Just hold it for a second. If we're here, that corresponds to this point, right? Right? Isn't that?
So that doesn't even make sense.
Window one there. It says 0. Well, you see the lambda that we calculated, it should be 0.05.
All right, just bear with me, class. I'll get to I'm not gonna worry about the values, let me just show you what's going on. All right, just listen up to this, all right? Just think about this logically. Normally, if we would get ZL, right, wherever ZL is, maybe this thing's 40. All right, I come into a point. Now, I'm at ZL, as I'm moving, I can only go towards the actual generator, right? So if I'm at the load, and I'm moving this, I think I said this wrong. If I'm at the load and I'm moving this way, I'm going towards the generator. So I'm trying to say this. So I'm at this point, I'm going to the generator. When I go this distance, whatever it is, until I hit the peak right here, that would be associated with this point. Now I'm trying to show you this. I'm sure it'll be this, right? Y'all with me? I don't know where the load is, but I'm just saying that would be the point. And you said we moved, is that right in the book? Is it 0.0246 lambda or not?
It's 0.0516 lambda. Yeah.
All right, does he have the maximum point at 3, is it?
He's got it at 1.9 centimeters minus 1.25.
All right, so this is not correct right here. And this drawing probably isn't correct here either. So let me do one thing to try to straighten things up. I don't want to spend a lot of time on this. I've already spent too much time on it, but if we have this drawing here, and I'm assuming this is where the load is, we know the load. And now we're going to have, according to his drawing, that's something that does, oh, I see why. He has something that starts over here and basically comes down, comes up, and then hits a maximum, right? The distance between here and here is what? This is where the maximum is. Just tell me. From where we located the load to that maximum. The distance, the difference between here and 3.9 centimeters, is that
Where
right
the
or no?
load goes to 0 and the max of Vmax is, let's say, 3.9.
This load is not at 0 though, is it?
Or it's where the load goes to 0. Isn't that
No, I want to go, we located the load at 1.1 centimeter, right? All right, from there to this point, what is it? Y'all hear me on this one? I'm not worried about
that's
this.
3.9.
This is total distance of 3.9?
Yeah, from that to the middle
Can
of the.
anybody confirm that? Is that right? It's not.
It's all open to approximation, so there's no one.
No, what is she going to say?
I think what this is saying is 1.9 minus 1.25.
1.25?
1.9 is the x, and then the.
Yeah, and then the other one is 1.25, and the difference between those two.
1.9 minus 1.25.
0.6.
That's a minimum, not a maximum. Isn't it? All right. That's the minimum. He goes to the minimum.
That's our issue.
He should have gone to the max. It doesn't matter. We can go to the minimum. Here's what he's saying, guys. Listen, just follow me on this. He's saying he's going not from here to here to the maximum, which would have been, I think, a little better. He's going to the minimum right here. Y'all hear me? Isn't that what he says in the book? Now, what's this distance difference between these 2 points from where the load is to that point? What is it, 1 point?
It's 1.9 minus 1.2, yeah, 1.9 minus 1.25.
1.9 minus 1.25 in centimeters. So what is that? Just tell me what that is and we'll get this thing done.
0.65.
So this is 0.65?
Yes, sir.
0.65 centimeters. Then divide that by 12.6 centimeters. Give that to me. It's
0.0516.
0.0516?
Yes, sir. That's what the book has.
All right, now, let me do it this way. If that's the case, now hear me on this one. I think I can make sense of it. The minimum is here, right? So it means this point right here is the minimum, is where we're at, right? If we're moving towards the actual load, we're going to be going in the opposite direction. Do y'all hear me on this, class? So if we do this, we're going to go with this radius, and we're going to go from this point here to the point, and now you're going to have to do this. 0.0516, subtract that from 0.5, and what do you get? Because every time you go around, you get 0.5, right? So this would be 0 or 0.5. 0.5 subtract your 0.0516. Go ahead.
Negative 0.448.
No. 0.5 minus 0.0516. Like a half minus 0.0. We can't be negative.
0.448.
All right. Can you confirm that? 0.448 lambda, right? Now, if that, and I'm sorry, I didn't know how he was doing it. I was getting smart. You agree with that? Just look at this is going to be wavelengths towards generator, not wavelengths towards load. Is it about that?
In the book, in the picture in the book, it says 0.351. I don't see that number, but
Wavelengths?
yes, sir.
Is this the wavelength he has in terms of how far we have to move or
Yes,
not?
it is.
That's what you got in office hours.
Huh?
That number is what you got in office hours when you did it.
I don't know if it's right in the book or not, but then if you got to move that far, right? This is the minimum. Y'all agree that's the minimum there? If that's the minimum and we're going towards the load in this direction, we're going in this direction, I'm going to go with this. Just tell me what the value is of ZL here. I'll take a look. Maybe I'm not seeing something that he's talking
It
about.
says ZL equals 0.55
Just-
minus. That's the.
No, just look at it right now. If you got a Smith chart, can you give me that? All right. I'll do it on the overhead next time for sure. I'll just have the whole thing for you done. This is not that difficult a problem. The whole idea is you got to estimate these things. What do you get for this value right here? If you go ahead, draw your circle with your compass, and then it has to go through 2, and then come over here and tell me what you get right here. When you just move from 0.0, this should be 0 in your Smith charts, or 0.5, you subtract that, you're going to get a value. I guess it's 0.448. I'm going with that one. I don't know if it's right. Now, what's this value for ZL? Once you take a look at that, it's going to have a real value and an imaginary value is negative. What do you get?
0.55 minus J.
0.55 minus J what?
0.25.
0.25. And if you multiply that by Z naught, what do you get?
28 minus J12.
Is that the answer?
Yes.
All right, that's the right answer. There's something wrong with what you're telling. So this actual value of ZL here is 28 minus J12, about 12 ohms. All right? I just want to say this one thing. All right? These problems can be irritating, especially. I didn't draw everything to scale here. And he's not estimating, but the whole idea is making you aware of this. Anytime you come in, you normalize load. Just think about logic. You normalize the load impedance, you put a dot somewhere, right? That's where you stop. You're at the load. Now, if you're moving wavelengths towards generator, you're moving this way. So you get a mile marker there, and you move. If they give you the voltage standing wave ratio and it goes to a maximum, you know that's how far you move. From here, the load, to that point. So you know how far it is. With me? If you keep moving a quarter wavelength, from that maximum, you're going to hit a minimum. It always does this. And if you get familiar with that, any way they frame the question, you'll be able to reverse engineer it. But you have to understand how that voltage standing wave, how the actual magnitude of the voltage appears based on measurements, and that's it. That's what he's trying to get you familiar with. I'm sorry, I think it's wrong in the book, that outside number, all right, which is, happens, okay? All right, now, any other questions? Gosh, I wasted so much time. All right, well, guess what we're going to do then? Match. Now, since we're going to do the quiz on Wednesday, it's probably going to have matching on it. I'm going to try to make this simple. I'm sorry about that. I did not mean to waste that much time on this problem. But I assumed that he was going to a voltage maximum. He didn't, unfortunately. And the information I get, it had to do with the minimum. Now, I'm going to level with you. This is simple. If you understand how we get the how we use a Smith chart to get the position of the load normalized, and then the input impedance at any point. I want you to watch this. This is called matching. And it's really impedance matching. We're spelled tuning, but I'm just going to use matching. What we're trying to do here is eliminate reflections. So at this point, what we want to get is a reflection coefficient after all is said and done down to 0. That's our goal. Nothing reflected. Here's how we do it. Here is ZL. Can be anything, and here's Z naught. And we're going to move a certain distance. I'll call this L of the through line. I'll just call it LT right here. So here's my Smith chart, draw it up, and you'll understand this, I think. If you've been keeping up, you'll understand. If you haven't, you're probably going to be clueless. But here's my Smith chart. Take out a sheet of paper, make sure you see this. All right. We come in, we have our load impedance. I'm going to just arbitrarily show you a point. I'm going to say this is ZL here. Doesn't matter where it is. You all with me? How many know how to do that? All right? Now, draw a line through here, and you're going to see something, and I'll call this really A, wavelengths towards generator. It's just a mile marker there, right? Now, if you take this and you draw a circle around here, go ahead and take your compass and draw a circle like so around here. This is going to have a constant magnitude reflection coefficient. You're going to notice one thing that's really important. It intersects this R=1 circle at 2 points, here and here. Can you all see that? Now at this point, the value of the normalized impedance is 1 plus JX. It's going to have an impedance value that's positive for reactive value. It's normalized here. If you kept moving, it would be 1 minus JX. Can everybody follow me on this? Now, we would like the input impedance, after all is said and done, of what we're looking at, to be equal to Z naught. So the reflection coefficient is 0. Do you understand that? So the goal is to make this thing look like Z naught. So if I move this distance, and I'm going to say that distance corresponds with this distance from here to here, LT, right? Now I have a normalized load impedance of 1 plus JX, don't I? Well, if I add something right here that had a value, normalized value of minus JX, then over here, I would have an impedance after you denormalize of Z naught. Do you all follow me on this? So now if I'm looking this way, this Zn would just be Z naught. So how do you get JX then? This would be with an actual component. Now remember, that's normalized. You with me, everyone? So think about this. If you have a capacitor, and I wanted to know what the impedance of this thing looked like, I'll call it ZC. Well, I know that Z, the capacitive reactance, is going to be minus J over omega C. Does everybody agree with that? When you normalize it, you divide it by Z naught. Do you all hear me? Just like we did with the load. We divide it by Z naught. So now I can say when I normalize this, I get minus J over Z naught omega C. And that would be the value of minus at Jx. Do you all follow me on this? Or I could say x is simply equal to 1 over, or I should say really c, not x, but the value of c for this case, if you take a look at this, it's pretty straightforward. If I want c right here, that would be 1 over z naught omega x. And that would be the value of capacitance that you could use to put in series and eliminate all reflections. Now you would need the correct distance and the correct value of capacitance. It assumes you know the frequency, and you'll notice that this only works for one frequency. You all with me on this, class? This is really going to be matching, and here it's with the series element. How many see this and understand the principle? Do you not? No, what don't you understand? Help me understand. You understand how I get this point right here. Let's start with what you don't. You agree? And you know, if you move this distance, you got 1 plus Jx. You would like to get rid of Jx, because if you do, then you're looking into something that has a normalized value of 1. You all follow me? So if you add a series impedance that has same magnitude, opposite sign, you'll get rid of that. So you think about it. That's a plus Jx. I want a minus Jx for sure. Capacitors have minus J, right? Minus J over omega C is the value, but you have to normalize it, and that's the reason you divide by Z naught. Do you all follow me on this? How many see this? All right. It should make sense to you. So if we just put a capacitor here with that value, we get rid of it. Right? Let me keep going. All right. What if I don't stop here? Remember, this is my circle of constant reflection code. Now I move, not to LT, I'll call it LT1. Now I move to LT2. I keep moving. Let's get rid of that capacitor now. I think you'll see it. Now I keep moving, and I go further, and I move to LT2. And now, at this point, I have a value of 1 minus Jx. Do you all follow me? How many do? All right, I got to get rid of minus Jx. What am I going to add in series? Well, in the impedance domain. Class? Plus Jx, and it's an inductor, right? So right here, I'm going to add a value of plus Jx. That's the value I'm adding. And I know what it is, the x value, because I'm going to read it off there. Y'all with me? By the way, these two will be conjugates of it. Whatever 1 plus Jx is, if it was 1, it would be 1 plus J1. Down here, it would be 1 minus J1. Just remember that. Now if I move there, I'm going to add an inductor. Do you all hear me? How do we calculate the value of the inductor? Well, you know the inductive reactance is J omega L, correct? But it's normalized, so we have to divide it by Z naught, and we set that equal to Jx, and you solve for L. You all see what L is going to be on this one? L becomes what? Z naught, right? X over omega. Everybody follow? Now, I've done that in series with impedances. You can also do it with admittances. All right, so I'm going to go through both, but I'm going to use elements for this because it'll be easier, I think, for you to see. So the next thing I'm going to do is erase this, and now we're going to do the same basic problem, only with admittances. I'll leave that up there. I'll erase this to give myself a fresh board. You're going to see that this, we'll do examples and stuff like this, but this it's easy to understand if you understand the Smith chart and what we've been doing with it so far. It becomes confusing as heck if you don't have it thoroughly understood. especially the next part I'm about to do. This is in his book, by the way. So now, what I'm going to say is I have this problem, but instead of impedance, I'm going to work in admittance. So I put my Smith chart up here. Now pay attention to this. This is a little tricky. You have Smith charts, you know what this looks like, right? Now, when I do this, I'm going to add an element, but it's going to be in parallel, not series. Parallel is called shunt also. So before we added a series impedance, now we're going to add a parallel. So we start, and I'll just do the steps. The first thing is find ZL, and that's going to be equal to really Z load, the actual Z load, divided by Z naught. That's where you come in, and I'm just going to assume it's right here. Well, actually, let me do it this way. I'm going to assume it's right here. So here's ZL. Y'all with me? Now, take your compass, doesn't matter where it is, and draw a circle. This is that old circle that we always draw. All right. We're going to add something in parallel, so we work with the admittance domain, normalized admittance. If that's the impedance ZL, you go straight through this thing to the other side. This would be YL, the admittance. It's 1 over ZL. It's normalized. Y'all follow me? Just want to make sure you follow me on this one. It's real important. Now we're in the admittance domain. Y'all follow? You remember admittances, right? You had this with Irwin's circuits class. 1 over Z is an admittance. 1 over R, you talk about a conductance, right? Y'all remember that? All right, now I move here. I come out and I take a look at this point. It's going to be something, I'll call it A, and it's going to be wavelengths towards generator. I'm there. Now we're going to move. We're at the load, but we're in the admittance domain. We're going to move until I hit either this point or this point, just like before. And I'll just call this point 1 and point 2. This point is going to be, and that would be a Y value of 1 plus J. I hate to use X, but I'm going to. And this is going to be 1 minus JX. That X is not an impedance anymore, it's an admittance. Do y'all follow me? They're just two locations. Now we're adding things in parallel. Admittances in parallel add like resistors in series. Do y'all follow me? So now, if I want to get rid of, I'm trying to eliminate the J business, just as before. But this is going to be with a parallel. So if I move from here, and I move all the way around until I hit here, and this would be, I'll call it B, wavelengths towards generator here. That's how far I need to move. So I'm going to move this distance in. Let me just do this way. I'm just going to call this L1. So I'm going to move this far, L1. Now I'm going to add an element in parallel. It's an admittance. Y'all follow. What value am I going to add? It's going to be minus JX if I move there. But this is a normalized admittance. I want to make sure I'm clear about this. Y'all with me? Now, when you think about admittances, they're 1 over impedances. So here, if you have an inductor, I'll put impedance, then I'll put admittance here. Actually, let me do it this way. I'm going to put L, and I'm going to put normalized impedance of L, and then I'm going to put C here. So if you take a look at this, for an inductor, if it's got a normalized impedance here, I just maybe normal Z. Normal Z right here. That's J omega L over Z naught. For a capacitor, it's going to be minus J over omega C Z naught. I'm just showing you what the normalized values of the impedances of those two components would be. With me? The admittances that are normalized are 1 over that. So over here, this becomes minus J Z naught. These would be normalized admittances. over omega L, and this would be simply J omega times C Z naught. Now the only thing I've done is take 1 over this quantity. You all with me? Those are normalized admittances. Here, if we went to the 1 plus Jx, we would want something that has a negative J sense. That negative J sense would be an inductor. Remember, it's in parallel. You all see that? So now I'm going to put an inductor down here, and I'll calculate the value in 1 second. So how do I get that value of inductor? This is the trickier one because you're not used to dealing with impedances. Well, I take this value right here, right? And I set it equal to minus Jx, whatever x is. You all with me, class? So I can say, for this one, I'm going to have minus J Z naught over omega L is equal to minus Jx. And you can see from this one, x itself, or really L would be equal to really Z naught over omega x. Do you agree with this, everyone? Let me just finish this thought. You with me? Just hang on for a second. How many see what I'm doing here and the reason for it? Now, what if I moved all the way to here? You understand how to get that point, right? Now you're going to move further, right? When I take a look at this, I have 1 minus Jx, right? I want to get rid of that Jx. I add something that's got admittance that's 1 plus Jx. What would that be? Capacitor. It's in parallel. Do you agree, class? How many see this? We just added an inductor in parallel, capacitor in parallel. When we move here, we kept going out, and I'm just about out of time. I am out of time. Call it L2. Now, I would take this value, J omega C Z naught, and I would set it equal to Jx, because that's normalized. Y'all follow me? And you would eliminate reflections. Now, one last thing that's so important. Don't ever put an inductor in parallel with anything that's going to have a DC offset of any. A DC offset, that would be a short circuit. You can't bias a bipolar with that. In general, anytime you deal with these things, you put inductors in series, if given a choice, and capacitors in parallel. Because inductor in series allows DC to flow. A capacitor in parallel blocks DC from shorting out. Now, we'll talk more about that on Friday. I'm going to give you some problems. Did you understand what I was talking about just now? Show of hands. All right, I'm telling you the truth. This should be logical. You're trying to eliminate reflections by eliminating that J business, and you got to land at the 1 circle in order to do it. Okay. See you next time. Sorry for taking so much time in that silly problem. Please make sure you do the homework. Some of you may not be here, but I'm going to tell you this much. This stuff will catch up with you.